This presentation is part of the TI-Nfocus AP Calculus video series. In this video, we'll discuss the chain rule, a specific concept associated with the 2017 AP Calculus exam free response question AB6. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm the former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by presenting some background information, and then use some intuition and interpretations to suggest or discover the chain rule. I'll present the formal statement of the chain rule, some common notation, and a very prescriptive procedure for applying this rule. I'll consider several examples in which we need to apply the chain rule. I'll use the chain rule to state the power rule. And finally, I'll look at several more examples of the chain rule in use. Here's a little bit of background information to lead us into the chain rule. Let's suppose we already have the differentiation rules for the sum, difference, product, and quotient of two functions. Consider a function capital F, which is defined to be x cubed minus 7x squared plus 3 raised to the 10th power. Suppose we want the derivative of f. Well, for now, the best we could do is to expand out that function capital F. We'd get a polynomial of degree 30, and we'd have to take the derivative term by term. There has to be a better, quicker way to do this. As I think about and search for a quicker way to find the derivative of capital F, I notice that it's a composite function. If I let f of u be u to the 10th, and g of x be that polynomial on the inside, then I can write capital F as f of g of x. That means that capital F is f composition g, or f composed with g. We need a quick way to find the derivative of capital F, which is f composed with g. Now, we can differentiate f, and we can differentiate g. So it seems reasonable that we can find a rule to differentiate that composition function in terms of f and g. In a very general sense, the derivative of a composite function f circle g is the product of the derivatives of f and g. And this is one of the most important differentiation rules called the chain rule. Here's an interpretation of the chain rule in terms of rates of change. du dx is the rate of change of u with respect to x, and dy du is the rate of change of y with respect to u. So if u changes twice as fast as x, and y changes 3 times as fast as u, then it seems reasonable that y changes 6 times as fast as x. And therefore we would expect that dy dx is equal to the product dy du times du dx. Here's a formal statement of the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function capital F, which is equal to f circle g and is defined by f of g of x, is differentiable at x, and capital F prime of x is given by this product, f prime of g of x times g prime of x. In Leibniz notation, if y is equal to f of u and u is equal to g of x are both differentiable functions, then we can write dy dx is equal to dy du times du dx. Here's a closer look at the chain rule. In words, this says that the derivative of the composite of two functions is the product of the derivative of the outer function evaluated at the inner function and of the derivative of the inner function. Now I think in order to find derivatives using the chain rule, you have to have good calculus vision. And that means you have to be able to identify the inner and the outer functions. Here's some common notation for writing the derivative of a composition function. Here's a very general procedure for finding the derivative of f circle g. First, use some good calculus vision to identify the outer function f and the inner function g. and then find the derivative f prime and the derivative g prime. And then finally, write the answer as f prime of g of x times g prime of x. Well, let's see if we can apply some of this theory. And I'll start by looking at the function that I presented at the very beginning of this video. Let's consider capital F, which is this polynomial raised to the 10th power, and let's see if we can find the derivative of this function. I have to be able to recognize that function as a composition, and I have to be able to identify the inner and the outer functions. After a little bit of thought, I can see that the outer function f is x to the 10th, and the inner function g is that polynomial. The derivative of little f is 10x to the 9th, and the derivative of g is 3x squared minus 7x. So I know by using the chain rule to find the derivative of capital F, I need to evaluate the derivative of little f at g and multiply by g prime of x. Here's another way to solve this problem using Leibniz notation, and this might be a little bit easier when you're first starting to use the chain rule. I'll begin by identifying the inner and the outer functions, and I'll let f of u be u to the 10th, and u equal to g of x be that polynomial. I'll find the derivative of each one of these functions. I'll find dy du and du dx. And then I'll put all of this together by finding dy dx, which is the product of dy du and du dx. And I need to finish this off by using the expression for u in terms of x. The chain rule certainly helps us find derivatives of complicated composite functions, but we also have to be able to use the chain rule very efficiently. And a way to think about this in applying the chain rule is that we start by taking derivatives at the outside and we work our way inside. The chain rule says that we take the derivative of the outer function evaluated at the inner function, and then we multiply by the derivative of the inner function. And here's this idea expressed visually with some mathematical notation. And here's one more way to think about the chain rule in words. When we take the derivative of a composite function, we start at the outside and we work our way inside, taking derivatives along the way. And after each derivative, we peel away that function and take the derivative of the next innermost function. Let's try a few more examples. First, let's look at the function y equal to cosine of x squared. I first need to recognize that that is indeed a composition function, and then I need to identify the outer function, which is cosine, and the inner function, which is x squared. To find the derivative dy dx, I take the derivative of the outer function, and I evaluate this derivative at the inner function, and then I multiply by the derivative of the inner function. And I just wrote my final answer in a little bit more common and appealing way. In part B, I need the derivative of the function cosine of x quantity squared. Once again, I need to recognize that this is a composition function, and here the outer function is the squaring function, and the inner function is the cosine function. The derivative dy dx is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. And I used a trigonometric identity to write my final answer. A common application of the chain rule involves taking the derivative of a function raised to a power. So if n is any real number and u equal to g of x is differentiable, then the derivative of u to the n is n u to the n minus 1 times du dx. And of course that's just a chain rule. We start taking derivatives at the outside and we work our way in. And here's another way we could write that derivative in terms of the function g of x. Here's an example of the power rule and the chain rule. Suppose f is a function whose definition is given by this expression. Let's see if we can find f prime of x. We first need to recognize that the function f can be written as a power function, and then we simply apply the chain rule. The derivative of f is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. And then I just did a little bit of simplification to arrive at this final answer. I wanted to show you a technology solution to this problem also. The TI-Nspire can actually find the symbolic derivative of this function f. So here I defined the function f, and then I used the derivative template to find f prime of x. Now the answer presented isn't in the exact form that I have on the previous slide, but nevertheless that's the symbolic derivative of f. Here's an example that involves both the product rule and the chain rule. Suppose f is a function defined so that f of x is equal to this expression. Let's see if we can find the derivative of f. We need some good calculus vision to solve this problem. The overall rule governing the derivative of f is the product rule. And then in order to take the derivative of each term, we'll need to use the chain rule. The derivative of f is equal to the first function times the derivative of the second plus the derivative of the first function times the second function. In order to find the derivative of the second function, I need to use the chain rule. And in order to find the derivative of the first function, I also need to use the chain rule. Then I did a little bit of factoring and simplification to arrive at this final algebraic expression. I can also use technology here to find this symbolic derivative. Here I define the function f, and then once again I use the derivative template to find f prime. Notice that the answer here is given to me in factored, simplified form, and even though you can't see the entire derivative on the screen, it is there if I scroll off to the right. This function f and its derivative are kind of complicated, so it's nice to be able to confirm this result graphically. I would suggest that we examine the graphs of f and its derivative to make sure that the relationship between these two makes sense. For example, as f increases, the graph of the derivative is positive. As f decreases, the graph of the derivative is negative. And where f appears to assume a local maximum or a local minimum, the value of the derivative is 0. This example involves an exponential function and the chain rule. Let's suppose that f is a function defined so that f of x is given by this expression. Let's see if we can find the derivative f prime of x. Once again, I think we need some good calculus vision. The outer function here is the exponential function e to the x, and the inner function is the polynomial function. To find the derivative f prime, I take the derivative of the outer function, evaluated at the inner function, the polynomial, and then I multiply by the derivative of the inner function. I found the derivative of the polynomial, and I just rearranged the terms to make this a little bit more visually appealing. We can also apply the chain rule to more complicated composite functions. So let's suppose that f is a function defined by f of x is equal to the sine of the cosine of e to the minus x squared. We need to recognize that this is indeed a composite function, and the outermost function is the sine function. We can apply the chain rule, and we start at the outside and work our way inside, taking derivatives along the way. And notice that there's a cosine function here, there's an exponential function, and there's even a power function. We start by taking the derivative of the outermost function, evaluated at the inner function, times the derivative of the inner function. This function is also a composite function, and the derivative of the outermost function is minus sine. We leave the inner function alone. And then we multiply times the derivative of the inner function. We continue to peel away functions taking derivatives along the way, and we're left with another composite function. The derivative of this expression is the derivative of the outermost function evaluated at the inner function times the derivative of the inner function. Finally, after a little bit of simplification, I'm left with this expression for the derivative f prime of x. Once again, I used technology to find this derivative. I defined the function f, and then I used the derivative template to find f prime. It's actually pretty amazing to me that a handheld graphing calculator with a built-in computer algebra system can find this derivative exactly symbolically. I think it's also a good idea to look at this result graphically. So on this screen I've graphed both the original function f and its derivative f prime. You might try to explain the relationship between these two graphs, and make sure that the graph of the derivative makes sense given the graph of the original function f. I hope this video provides some insight into and some good problems associated with the chain rule. And just one final reminder, there are lots of valuable resources on the TI website. There's material there involving technology, calculus, and other math topics.